Okay, let's make a basic transformer circuit and demonstrate that. So here's a new schematic, and transformers are made with inductors, so we'll grab an inductor and we'll flip this one by mirroring it, put it here. They can be drawn anywhere on the page, and you can have as many as you want. They'll be coupled with a command using this little OP operation, spice directive. And in this, we'll use the K command, which is a coupling coefficient. And K for transformer number 1. And move this out of the way so you can see. The first inductor is L1, another inductor is L2, and if there were more inductors, we just add them to the list. And then last thing you put is the coupling coefficient. And for binocular cores, I like to use 0.9975 because it's pretty close. And then you just plunk this down somewhere, wherever. And then we're going to add a voltage source to drive it. Put it over here and add a load. And then we're going to wire those up. Click, 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 click. Okay, and in the previous video, I mentioned that every isolated loop in a circuit has to have a ground somehow, has to have a path to ground in it. And if it doesn't, you need to put one. It could be the center tap of a transformer or some other circuit point, but it needs to have a ground path in order for a spice to always converge and run correctly. All right, it will tell you if it needs one. All right, now we need to, on this transformer, we need some winding inductances. So let's set the primary to 100 microhenries. And let's move that text somewhere. And then let's set this secondary to 400 microhenries, which corresponds to a turns ratio of 2 to 1. Since the inductance is proportional to the square of the number of turns, 2 squared is 4, so this is a 2 to 1 transformer. And let's move the 400 microhenries out of the way. Okay. And then let's set the load resistor value to 50 ohms. To set a component value, you move the cursor over the component until you see the little hand, and you right-click on it, and you can put in the value. If you're not in the right place, like if you're here and you click it, you'll be editing the text instead, or some other parameter, like the reference designator here. Okay, so you have to be over the component. For the voltage source, advanced, in this circuit we're going to run an actual sine wave. Rather than, we're not going to be doing a frequency sweep, we're instead going to be running a real signal through and simulating the response, looking at the response. So let's set this to an amplitude of 1 volt. That is 1 volt peak, and set a frequency of, say, 10 kilohertz. Okay, and then move that text somewhere out of the way. Okay, and now we're ready to simulate, we think. We go up here and hit the simulation, and this time we use transient analysis. AC analysis is for frequency sweeps. Transient analysis is for real-time simulation. We'll run 5 milliseconds of simulation, and these other items you don't really need to worry about for this time. Something I use occasionally is maximum time step when I want to guarantee a high resolution. Usually when I'm doing an FFT or something, then you want to set the time step to something small like a nanosecond. Otherwise, just let the circuit simulator adjust the time step as needed. So what we'll do here. Okay, now we get this error as soon as we do this, because we have a situation, and I wanted you to see this, where we have a voltage source, which is a perfect voltage source, 0 ohms internal, and a perfect inductor in parallel. The voltage source is going to tell the inductor this is what voltages you're going to have, and the inductor is going to complain about that with infinite currents. So to fix that, you need to insert some resistance. And the easy way to do that is either to add a little resistance here with some series resistance, or to give the generator a source resistance, which let's just make this a 50 ohm generator. And now everything should be happy. Okay, now remember that we have a 50 ohm source here. Let me move that R serial parameter so it's not overlapped. Okay, remember you have a 50 ohm source here, and we have a 50 ohm load, but we have a 2-to-1 transformer. So this 50 ohm load actually looks like a 12.5 ohm load to this, if the transformer is working correctly. So what we would expect to see, instead of 1 volt here, we should expect, instead of half a volt here, a 50 ohm load, we have a 12.5 ohm load, so we expect to see a 1/4 of a volt instead. I hope I said that right. Anyway, you get the idea. Let's run this and see what happens. Okay, it's done. Now let's go down here and pick the thing to look at. The output voltage we can get simply by pointing to this node here and clicking on it, and it'll give us the output voltage. But if we put the cursor over the resistor, we see a current symbol, and if we click there, it would give us the current through that resistor. We can also get the current through this inductor, which should be the same as this current, and the current through this inductor, or the current through this voltage source, or the voltage up here. Or we can pick all of them and plot them all on one drawing. So here we can plot the voltage here. There's the output voltage. And we can see that the amplitude is the lower left corner, 200, basically 200 millivolts. Okay, and the hopefully that works out correctly for the turns ratio that I gave it. And so for some reason that seems wrong. It should be 12.5 and 50. Should be 12.5 over 62.5. Let me calculate that real quick. 12.5 vectors. Yep, 200 millivolts. That's correct. Spice is not lying. And then we can also add this voltage. There it is. It's now plotted on top of this one. If you want to delete that voltage, you go up here and right-click and say Delete Trace. If you want to put it back, click it there. If you want to see this current, boom, we add the current, and it's plotted over here, and it's the red one. So it's sitting in the little over 4 milliamps. Get the peak current here. It's 4.1 milliamps peak. Maybe there's some inductive peaking going on there or something. Anyway, it seems like it should be 4, just based on round numbers. But we can remove the current. Okay, so that's a basic transformer. As I said, the transformer windings can be drawn anywhere, on top of each other, next to each other, or across the sheet from each other. It's this coupling coefficient that determines how they're coupled. If we were to add another transformer over here, couple of windings, we could add another coupling coefficient. It would be K2, L3, L4. 1 is a perfect transformer, coupling coefficient of 1. We can put that here and do something with it. So you can have as many transformers on the page as you want. When you add the transformers, you get these phasing dots, as soon as you create the coupling coefficient, these phasing dots appear. You can flip these inductors or pictures any way you want. If I grab this and, oops, need to grab it. Grabber, grab, and then rotate. You now have the dot on the top, like that. However you want to do it. So that's a basic transformer. In the next video, I'll show you how to make a transformer with parameters so that you can enter the number of turns and have it calculate the inductances for you, which is usually what you want to do rather than figuring out the inductances and putting them on the transformers manually. Okay, that's the end of that one.